Good afternoon. This is Rob Sparks, and I'd like to welcome you to this edition of Live from NOIRLab at Kitt Peak/Tucson. I'm your host, and I'd like to, we have our moderator, Jamika Marshall, in the chat room. She'll be taking your questions and comments there. Our guest today is Parker Fagrelius of NOIRLab in Tucson, and I'm really excited because Parker works on the Dark Energy Spectroscopic Instrument, also known as DESI, and today she's going to talk about creating a 3D map of the universe with the Dark Energy Spectroscopic Instrument, i.e. DESI. It's a really neat project, and I'm looking forward to hearing about it. So remember, if you have any questions or comments, you can enter them in the chat box, and we'll relay them to Parker. First, I'd like to tell you about a little Kitt Peak National Observatory, for those who might not be familiar with it. Kitt Peak is funded by the National Science Foundation and is a NOIRLab facility. It was founded in 1958 and is located about 55 miles southwest of Tucson, on land leased from the Tohono O'odham Nation. We're indebted to the O'odham people for letting us use one of their sacred mountains for astronomical research. Kitt Peak is home to over 24 optical telescopes and 2 radio telescopes. Now, normally we highlight a science or recent press release from Kitt Peak, but this week I want to do something a little bit different. I'd like to share a recent image from Kitt Peak. Although the observatory is closed due to the COVID-19 pandemic, there is an all-sky camera in operation on Kitt Peak. This camera is operated by the Spacewatch Observatory. Spacewatch has 2 telescopes on Kitt Peak that do research on near-Earth objects, including potentially hazardous asteroids. Spacewatch is operated by the University of Arizona. Spacewatch, on Thursday, September 17th at about 10:52 p.m. Tucson time, the Spacewatch all-sky camera captured a very bright meteor, also called a bolide. This meteor was bright enough to illuminate the observatory domes in this image. These domes are being lit up by the meteor. There was no moon in the sky at the time, so it would have been very dark without the light from the meteor. This meteor was reported by over 24 people to the American Meteor Society. They have a Fireball report page. If you Google the American Meteor Society, you can see the reports of this meteor, including this image, and one other image was captured by an amateur astronomer in Tucson from an all-sky camera at their observatory. So I thought this was a very interesting image to show off here for the Kitt Peak. So now to meet our guest. Parker Fagrelius currently works as an operations supervisor for the DESI project at NOIRLab in Tucson, where she started about a year ago. Previously, she had been at Berkeley Lab, where she received her PhD in physics for work on the DESI focal plane. Before attending UC Berkeley, she worked at Jet Propulsion Laboratory, where she was the project manager for the optical communications payload that was mounted and operated on the International Space Station. So I'm going to stop sharing my screen now and bring on Parker so Parker can take it away. Parker, you there?
Hello.
Hello. And I will mute myself out and let you share your screen in the presentation.
Great. All right. Get everything started here. All right, thank you, Rob, for the introduction. Again, my name is Parker Fagrelius, and I'm a scientist here at NOIRLab in Tucson, and I'm going to be presenting on behalf of the whole DESI collaboration, which is a large collaboration across the globe. So I want to tell you about DESI and how we are creating a 3D map of the universe. You can see this image, this first image here is from Kitt Peak, and the big beautiful dome you can see is the Mayall telescope, and that's a telescope that DESI is installed in right now. So we will get back to that more. All right. So here's the outline of the talk. Pretty much want to break it down into the dark energy side of DESI and then the spectroscopic instrument. Dark energy is a large topic to cover in a short amount of time. So really what I want to do is motivate the DESI goal of measuring the redshift of up to 35 million galaxies. And then once we've established kind of the motivation for why we're building a spectroscopic instrument, I'll get into the details of what that instrument looks like and how we're using it. All right, we'll start with the basics. What is the universe made of? Well, we can break it down into protons, neutrons, and electrons. And we call this ordinary matter or baryonic matter. Oh, and I'm going to change the gallery so that you can see the main. Apologies for this. Hopefully we can get the main slides up and being shared. Let me know if that looks a bit better. Okay, great. Let me continue. Okay, so universe is made up of ordinary matter, protons, neutrons, electrons. They build atoms, atoms build molecules, molecules build humans, for example, also chairs, planets, galaxies. Pretty much everything we see in the universe is made up of baryonic matter. And if we zoom out, way out, we find that with the approximately 100 billion galaxies in the universe, the large scale structure of the universe is not random. These galaxies are not spread around necessarily in a random way, but they form kind of a cosmic web. And so we're interested in exploring this large scale structure of the baryonic universe. And this was created with galaxies measured with the Sloan Digital Survey, measuring the redshift of many, many galaxies. And so DESI's really going to be building on top of this and creating the next best 3D map of the large scale structure of the universe. So we're really just focusing on so far just on astrophysical objects that we can see and we can measure. And one of those types of astrophysical objects are supernova. So when a star comes to the end of its life and it is a certain size and has other attributes, it might explode into a supernova. Supernova are interesting to study for a variety of reasons, but one of them is that a specific kind of supernovae that we call type 1A all seem to have the same brightness when they explode. We know that different stars have different intrinsic brightnesses, but if a star gets to a certain size and explodes into a supernovae, then they're pretty much all the same brightness. So they're easy to measure because they're very bright. We can see them. And so we can use them as tracers for how the universe is expanding or not expanding over time. And about 2 decades ago, a couple different groups were looking at similar things. They were measuring the brightness of supernova as a function of how quickly they're moving away from us, AKA redshift. And what they found was not what they thought they would find. They thought they would find that actually the universe is slowing down in its expansion. What they found is not only is the universe expanding, but it's accelerating in that expansion. It's getting bigger, faster and faster. Now they were measuring the brightness. You see on the y-axis of this plot here, effective MB, that's the brightness, the magnitude. But the magnitude of the supernova and the distance away from us are correlated. As we said, they all pretty much have the same intrinsic brightness, and they are what we call a standard candle. I'll get more into what that means. But essentially this plot is showing how quickly something is moving away from us, the redshift, versus its distance away from us. So that's the X versus Y. And if we generalize that plot, then we find that the relationship between redshift and distance of objects really depends on different components than just the supernovae or just the objects that we're measuring. It also has to do with how much dark energy or dark matter is involved. Now, we haven't gotten into what dark energy and dark matter are yet. We'll get into that in just a second. But depending on this relationship between how far away something is and how quickly it's moving away from us, we can start to constrain our understanding of the properties of these different elements that make up the universe. So we really want to measure distance and redshift to learn more about these different components. So what is dark energy? It's not in my opinion, it's not a great term. It's a name we give to the phenomenon causing the acceleration of the universe. It's a great term from kind of a sci-fi perspective, but it really leaves a lot to the imagination. And we don't really know what dark energy is. We can't measure it. And it doesn't have a gravitational pull like dark matter does. Dark matter is distinct from dark energy in that even though we can't see it, we can see that it does have mass, and it has gravitational pull on other mass objects. But dark energy is the thing that gives rise to this acceleration of the universe. Now, back in the day when Albert Einstein wrote down his theory of general relativity, which really provides the framework for our understanding of cosmology, gravity, so much of what we understand in the universe, he had to include a little fudge factor. Now, this equation, I don't expect anyone to remember this or to pick apart what all this means, but he put in this fudge factor here we call the cosmological constant. And it bothered Einstein because there was no seeming physical motivation for this. He just needed this fudge factor in there for the equations to balance out in a way that made sense for real physically motivated phenomena. And so for a long time, it really was just this constant that was put in the equations. But once the identification of the acceleration of the universe was found, it was thought perhaps this cosmological constant actually does have physical motivation. Perhaps dark energy is the cosmological constant. But that's only the case if, in fact, it doesn't change in time or space. And so we really want to understand, is dark energy static? Does it not change over time and space? Or does it? And in the event that we find that dark energy does change with time, then we need to modify the theory of general relativity. So these are big questions for the cosmological community. What you see on the right, this pie chart here, is a breakdown of the energy density of the universe. Now, everything we see, including all of the 100 billion galaxies in the universe, only makes up less than 5% of the energy density of the universe. The majority is made up by this dark energy. But this has changed over time. And you can imagine as the universe has expanded, the density of ordinary matter becomes less and less. But if dark energy is constant, then its density remains the same. And so if we continue to move forward and dark energy is in fact a cosmological constant, its piece of the energy density pie will only grow. But we're trying to understand what is the situation right now and what did it look like in the past. And then of course that can give us some clue about what happens in the future. So if we want to study dark energy, then we would want to measure it, but we can't measure it directly because we can't see it and it's essentially unmeasurable. So what we can do is determine how it impacts the universe over time, how it impacts the expansion history of the universe over time. And that expansion history can really be drawn out by a couple attributes we were just talking about, the redshift of objects and the distance away from us there are. And so by measuring things that we can see, things that we can measure, we can start to constrain our understanding of dark energy. And with the measurements of redshift and distance of many, many astrophysical objects, we can create a 3D map of the universe, which will help us then understand the attributes of dark energy. So what the DESI instrument will be focusing on is measuring the redshift and distance of certain objects, aka galaxies. So what is redshift? Just to give everyone a refresher or introduce the concept for the first time, it's very similar to the Doppler effect. If you have a car passing by you, you hear something like, oh. the frequency of the sound coming from the car changes as the car moves away from you or as it's approaching. Light does the same thing. So as something emitting light moves away from you, the wavelengths are redshifted. They are moved into the redder part of the visible spectrum we call red, and then of course it could move into infrared and even further. If a galaxy were moving closer to us, then the light would move to the left towards the bluer wavelengths. You can see this pretty well in this plot right here, where we have the emission from a galaxy or star, and there are certain elements being in the galaxy that emit light at very particular wavelengths at rest. And so this is what we would see from a galaxy that is just sitting there or very close to us, let's say. But as that galaxy moves away from us, these recognizable emission lines can be seen in the red. So by comparing the 5,000 angstroms that we would measure the galaxy at rest to where we actually measure them here, we can determine the redshift, which we denote by Z. So by measuring the spectra of galaxies as they move away from us, we can precisely measure the redshift using a spectrograph. Okay, so that's redshifts. Next is distances. We already covered this a little bit talking about type 1a supernova. They are what we call a standard candle. So you can imagine you're sitting in a room, you have a candle sitting right next to you, and then you set one across the room. You know that their intrinsic brightness is the same, and the dimmer the one on the other side of the room is can tell you about how far away it is. Same thing with type 1a supernova. They have almost the same exact brightness. And so by the dimming effect of the type 1a supernova as it's further away from you, you can determine how far it is from you. You can measure the same thing if you had a ruler. If you have a ruler right in front of you, it subtends a certain angle. If you move it across the room, it subtends a smaller angle. And comparing these two angles can tell you exactly how far you have moved the ruler, or the two rulers are away from each other. The tricky thing about standard rulers is that most astrophysical objects are not standard. If you've come to other talks like this, you realize that the objects in the universe are incredibly diverse and very unique. So no two galaxies are really alike. And in fact, type 1a supernova, as they are quite similar, they're not exactly the same brightness. There are differences. And so we need to be very careful in choosing a standard ruler. And there wasn't really a great standard ruler for quite a while in cosmology, but then one was discovered called Baryon Acoustic oscillations. And so this is a standard ruler that DESI will be using. And the idea here is that the separation of two galaxies is not purely random. There is a greater than random chance of finding two galaxies separated by a very specific distance. I'm choosing those words carefully, saying more than random. And by doing so, I hope some things are going off in your mind like, oh, statistics. We're really talking about there's a statistical chance that you're going to find two galaxies separated by a certain amount rather than randomly. And the reason for this goes back to the early physics of the universe. Early on, the universe was kind of a soup of some baryon matter, like electrons and photons, all bumping into each other. And there were some quantum fluctuations in this soup, and then those fluctuations turned into waves that started moving out in basically at the speed of sound. That's where the word acoustic comes from. As the universe expanded, it cooled down, and at a certain point, it was cool enough that the photons flew off and flew away from the baryons. And those photons are what we call the cosmic microwave background. The cosmic microwave background told us this is exactly how far everything was away from each other in the very early universe. And the baryons stuck around, became the seeds of the galaxies today. And so we know that there's a very exact distance that that wave traveled in the early universe, constrained by very simple physics, in fact. And so as the universe expanded over time, we can track that distance away from each other as a function of time and hence distance. And so we are using this distance away, the more than random chance of finding two galaxies close to each other, as a standard ruler. In order to do that, we need to have the measurement of a lot of galaxies. In order to use this ruler effectively, we need to measure as many galaxies as possible. And so that's really the pursuit that DESI's after. So this is the motivation for measuring the redshift and the distance of 35 million galaxies or more. So I hope that has in some way, in a very quick way, given the motivation for measuring the redshift of a lot of galaxies. I understand we rushed through the concepts of dark energy and cosmology and BAO very quickly, but hopefully at least it has convinced you that we need to measure the location of a lot of galaxies in order to better understand dark energy. So at this time, I'm going to shift over to how we're going to measure redshift and distance. And so that brings us to our spectroscopic instrument. An instrument really takes the light from a telescope, which is essentially a light bucket, and measures it in a way that's useful for some scientific goal. There are many different kinds of instruments, but essentially every instrument takes light and turns it into a measurement that's interesting or useful. Many instruments are just cameras. That is a useful way to capture light for scientific goals. In the case of DESI, we use spectroscopy. So we take that light, and instead of measuring it as an image, we take it and we spread it out and look at the light as a function of wavelength. Now, we're not the first to do this. There's a long lineage of large spectroscopic redshift surveys. The most recent being BOSS and eBOSS. These are projects that are run at the Apache spot in Sunspot, Arizona, on the Sloan Digital Survey telescope. And they measured up to 3 million redshift, which was at the time, you know, the leading order, really. And the way they did this was they took aluminum plates and they stuck fibers in pre-drilled holes that are aligned with different galaxies given a location on the sky. And those fibers were plugged in manually by people. And so really when we wanted to move up an order of magnitude, going from 3 million now to 35 million galaxies with DESI, we needed a new way to do this. Having manual insertion of fibers into these plates just is not feasible when we want to move up to the next level. So DESI is really on line to be the next on a well-traveled path of large spectroscopic survey. Together with PFS, it's an instrument that will be going on the Subaru telescope in Hawaii. And Euclid is a space mission run by ESA. So DESI is kind of leading the pack here and hopefully providing some good lessons learned for additional projects that come soon. So before we can measure the redshift of objects, we have to know what we're looking for. We have to identify the targets. We need to know where the galaxies are. And so for many years before this, there were several surveys going on to identify all of the targets for DESI. 3 of them, one DECALS, MZLS, and BASS. DECALS was run on the dark energy camera, which is being used for the dark energy survey on Cerro Tololo. The Blanco telescope, where the dark energy camera is actually the sister telescope to the Mayall telescope. So it's really great to use both of these telescopes. And so the Blanco being in the southern hemisphere. MZLS and BASS were both run off of Kitt Peak. So using these surveys, we were able to take lots of images of the sky that we would like to use with DESI and identify different galaxies that we want to find the redshift of. And I highly recommend visiting this website right here, legacysurvey.org, because all of the images taken from these surveys are available to the public, and you can just look around the whole data set with a viewer very similar to this. And each one of these blue circles here represents a fiber that DESI will be using. So everything within that circle could be targeted for a DESI galaxy and a DESI redshift. But I really recommend looking around on this legacy survey. It's incredible, all of the images that you've captured, and you could really find some brand new objects yourself. So that in and of itself was a very exciting project, but has now established all of the targets we need to move forward with DESI. So now let's take a look at DESI. So this picture right here on the left is the Mayall telescope. It's really a beauty. Hopefully when COVID is a bit more manageable and Kitt Peak opens up to visitors, hopefully you all can have a chance to go take a look. But right here is where the primary mirror is. It's a 4-meter telescope. And so when the dome is open, the light will come down, bounce off the primary mirror, and go into what we call the prime focus. And right here at the prime focus, we first have corrector lenses. So a set of large lenses that adjust the light to make sure it's just about perfect. There are many aberrations from both the telescope and from the atmosphere, and all types of things that can make the image look a little wobbly or have chromatic aberrations. And so these lenses help correct all of those little offsets. And then once the light goes through these offsets, goes through these large lenses, it makes it to the focal plane, which is here. The focal plane is made up of 5,000 robotic positioners holding fibers. And we'll show you more pictures of that. So the light from 5,000 galaxies will bounce off the primary mirror, go through these lenses, and then go into individual fibers. Then from the very top of the telescope, the light will curve down the telescope through fiber optics, about 40 meters of fiber optics, and then enter spectrographs, which are kept down here in a very cool room to make sure that they're very stable. And then from there, the light is spread out so we can measure the redshift. Here is some pictures of moving the old corrector out that was used prior to DESI and putting a new one in. We wanted to expand the field of view to 3 degrees. And so we needed to include larger optics than were already available. So you can see this giant crane putting the new corrector frame in the telescope. These are the lenses that you saw before. And then those lenses are all put into a corrector barrel. And this is what's actually mounted at the top of the telescope. This stuff on the side here is used for focusing. So if things warm up or cool down, we can slightly move the lenses so everything stays in focus. Here's a little more view of the focal plate instrument. So again, I said there are 5,000 robots. Each one, the whole focal plate is kind of separated like a pie, and each slice of that pie has 500 positioners. It has a guide or focus camera mounted on the side of it. That's here. And so the fibers are attached to these robotic positioners, which can move the fiber tip anywhere within a 12 millimeter diameter circle. Now these circles overlap one another. And that's so that we can make sure we can hit any space on the focal plane. But it does mean that we have to make sure we don't run into, have the fibers run into each other. So all of that is done with software very carefully, making sure we put the fibers exactly where they need to be without running into the other positioners. Now, and before sending them up, we have to do quite a bit of testing on each one of these petals. On the back side here, you can see lots of fibers and wiring, and it can become quite a mess, but it has, the final design is quite beautiful, and we have found that it works, which is great. So this is me in the lab back at Berkeley before essentially moving with the whole instrument to Tucson. Now I'm going to try something that often doesn't work, but I'm going to try a video, which means I need to share another screen. So bear with me for just a second. Okay, so going to show kind of how the positioners move. See them move in one direction and then another. Move again. And there we go. All right, so each robot has two unique motors on it, and that enables it to move anywhere within the 12mm distance. Okay, let's go back to the slides then. Okay, I imagine that we want that one. Okay. All right. So once the light goes into the fibers, then it's carried all the way down to the spectrographs. I said with a 40-meter optical fiber. Now the optical fibers are about the size of human hair, maybe a little bit bigger, 100 microns in width. They're not very easy to work with, I can tell you that, but they are very effective at carrying light. And one of the decisions that Desi made early on was not to use connectors, but instead to splice fibers together. And what that means is when we installed the focal plate, we had only about 3 meters of fiber connected to the focal plate. And then we connected that 3-meter piece of fiber to the additional 40 meters of fiber by heating them up and essentially gluing them together. So that's what this picture is right here. You can see the fiber has some covering on it, and we take away the covering. We cut both ends of both fibers very exactly, and then we put the two fibers together. We essentially melt them together, splice them. And the reason we do this is because we want to lose as little of light as possible. And when you use connectors, you do lose additional light. So we're really trying to get every possible photon from those galaxies down into the spectrographs. So, a couple more pictures here. You can see here these big, thick black cords. Those are actually the fibers. So they're very well protected, and that's how they'll travel all the way down spectrographs. And then once they get to the spectrographs, the fibers are all thinned out and installed. Okay, it looks like we have a question.
Hello, yes, Parker.
Yeah.
I like to say aloha to everyone in our YouTube chat. And we appreciate all of your questions and comments. So we do have a couple of questions that we'll hold to the end at request of the person asking the question. But we do have a question from Leonardo Paredes, and Leonardo asks, how close the fibers could be, how close in arc seconds could the fibers be to each other?
Okay, yeah, that's a great question. Let me see if I can't go back a couple slides to looking here. So each one of the fibers is held at the very tip in a glass ferrule. And so that extends the size of the fiber. And so they certainly can't get within 50 microns of one another, but they can get within, trying to think exactly what the arc second distribution is, but they can get quite close to each other. So the ferrules, I want to say, extend about 1 millimeter on either side. And it's 70 microns per pixel. I'd have to go back and look exactly, but they can pretty much get as close as the ferrules are to one another. Sorry, I don't have the exact number for you in arc seconds, but it's quite close to overlapping.
That's perfect. Thank you so much, Parker. For sure. I'll come back in a little bit with more follow-up questions, but hopefully, Ariel, that answered your question.
Okay,
thank you so much. And we have more comments on that topic. I'll come back on it. Thank you.
Okay, excellent. I only have a couple more slides here, so I'll continue there and then come back to those questions. Okay. Okay, so once the light is inserted into the spectrographs, then it's spread out, as we've discussed, with a dispersing element similar to a prism. You know, if you have kind of like a prism in your house and you see rainbows, it's essentially the same thing that's going on. But we have 3 different cameras, and the reason for that is different cameras are sensitive in different regions of light. And so we have a red, a blue, and an infrared camera so that we can get the most efficiency for certain parts of the whole spectra. So here you can see there are 10 of these spectrographs, one for each petal. So 500 fibers go into one spectrograph, and then the light is split up for the 3 different cameras. And then we should not forget about the data, of course. We'll be generating a lot of data. We have to be efficient in our observing because we want to measure the 35 million galaxies over about a 5-year project. And we want to repeat measurements several times so that we get the best possible measurement. And so this is going to generate about 10 terabytes of raw data every year. And that data goes from Kitt Peak to computers at Lawrence Berkeley National Lab called NERSC. So we expect about 100 terabytes of data when the 5-year project is over, because we take that raw data and we turn it into more useful products. So this supercomputer NERSC will really make it possible for approximately yearly availability of data. So we expect the data to be available to the public about once a year. And so what's exciting is that not all of this is just planning anymore. We've actually made it work. So DESI is installed and working for the most part. October of last year, we got first light. So we had light coming down the fibers. And so at that time, the instrument wasn't fully commissioned, meaning not all parts of the instrument were yet fully working at the level we'll want them from the spectrograph, but we could certainly point the fibers at galaxies. And so what we did at the beginning was just point the focal plate at very large objects, one being California Nebula. And so we got different light down each one of the fibers. So we didn't point each fiber at a different galaxy, but we really looked at one large object. But the spectra we're getting already is very exciting. So what you see here on the right is we took the spectra coming in each one of, let's say, this petal down here that was looking at a specific galaxy. And we just took the H alpha line. So we just took what's the brightness in that exact area. And so you can see the distribution changes across the fibers. It was very exciting. And already we have hundreds of thousands of spectra. It's really almost amazing how quickly we can amass hundreds of thousands of spectra. So even during commissioning, when we really aren't working at our highest efficiency, over just about 2 months of running, we already have a lot of data that we can work with, which is great because we were shut down in March, and I'll talk about that on the next slide a little bit. But the commissioning project was almost done at the end of March, really getting us all ready to be able to complete our 5-year survey to get the 35 million galaxies. But like I said, we were shut down in March due to COVID-19. We started ramping up activities in Mail again this month, which is very exciting. In the meantime, we were working with those hundreds of thousands of spectra that we had, making sure we improved our tools and our understanding of how to run efficiently and get ready for when we're back online. And we're going to have to do some recommissioning for the first couple of months that we're up there, make sure everything's still working as expected. Then we'll move into survey validation phase. And survey validation is really, are we looking at the right objects on the right cadence, and kind of make sure we know how the whole 5 years should run. And then we will dive into the full survey probably in the summer of next year with the public releases of data every year. So that is the last slide I have. Please visit our website, desi.lbl.gov, for updates and getting to know different members of the DESI team, etc. And so here I will stop for questions. All right, Jamika.
Thank you, Parker. That was great. Well, I'm sure Jamika will be here in just a minute, but I actually have a quick question I think might be of interest if you'd like to just address. This is actually funded by the Department of Energy, isn't it?
That's right. It's a collaboration between Department of Energy and the National Science Foundation. So Lawrence Berkeley Lab does have a physics division, and so they're looking at dark energy. It is a form of energy, I suppose, but yeah, they do support physics pursuits at the Department of Energy.
I just thought that was an interesting thing to note because that's an interesting partnership that's going on with us here.
Yeah, so. Absolutely.
Jamika, are you back with questions from the chat? There she is.
Hello. So I apologize. It is raining very hard here, and so it is very, very loud, and so I am unable to hear everyone very well, so I apologize for that. But yes, thank you so much, Parker, and we do have some questions here in the chat that I was asked to hold to the end. All right, so here's the first one. So our first question here is, why use the hypothetical dark matter that does not have an isotropic and homogeneous behavior? That's from Ariel Vallejo. Thank you, Ariel.
Can you ask that question again?
I'm sorry, what's that?
Can you repeat that question, please?
Yes, let me type it in the chat for you.
Okay, great.
Yes, the good old Hilo rain.
Okay, so I've dropped the question in the chat, and the question again is, why use the hypothetical dark matter that does not have an isotropic and homogeneous behavior?
Okay, so we are actually not necessarily measuring, we're measuring the distribution of dark matter in the way that it follows or has seemed to follow all baryonic matter. But we're actually measuring the location of baryonic matter, the redshift of galaxies. And that information is helping us better understand dark energy. So I hopefully that somewhat answers your question. I'd also say at this point, the kind of standard cosmological view of the universe is that it is made up of dark energy, dark matter, and baryonic matter. Dark matter is not considered in the cosmological community right now as being hypothetical. It is not exactly understood what it is made of. It hasn't been measured in the lab or at CERN where they're trying to actually measure what is dark matter. But there is general consensus that it does exist. We just want to figure out what it's actually made of.
Thank you, Parker. We have a few other questions, if it's okay to continue really quickly.
Of course, yeah.
Fantastic. Okay, so our next question is, well, it goes to DESI. Let me skip a question. And the question about DESI is, would DESI time be available for other projects other than the main dark energy survey?
That's a great question. So one of the interesting things about DESI is that it will be the only instrument on the Mayall telescope for the next 5 or so years. That's unique because most of the biggest instruments or biggest telescopes in the world have several instruments on them. Part of the reason why the DESI project chose the 4-meter telescope at Kitt Peak was that there's perhaps a little less competition for use of the 4-meter telescope than 10-meter telescope, like one of the Keck telescopes. And so it was a possibility to use all of the time. Now, over the next 5 years, the DESI project, the DESI collaboration, will be using all of the time available on the telescope. However, I'll say these two things. One is that the data coming from DESI will be available to the general public and so for other working groups at least once a year. And there's so much information in that data set that most certainly the DESI collaboration isn't going to be able to understand everything that's in that data on their own. And so that data will really be used, I hope, by the greater astronomy community. The second thing I will say is after 5 years, once the survey is complete, the instrument, as I understand it, is transferred to the National Science Foundation in a very similar way that the dark energy camera was. And so at that time, we don't know exactly how it will be used, but it's very possible that at that time, it could be used by any other group.
Excellent. And we have a few more questions. One here is, how large of an area will it cover, and will then this be achieved?
Yeah, give me 1 second. I want to make sure I get the right value here.
Thank you. Yeah, we appreciate you so much being on the show today. Definitely a very engaging and popular topic for sure, Parker.
Good. I'm glad. I'm in this field because I think cosmology offers some really interesting questions to explore. So the DESI survey will cover 14,000 square degrees. And most of that space, it will cover more than once, up to 5 times. Some of the brighter galaxies or the galaxies that are closer to us will not need to be returned to several times. But for the most part, the galaxies will be repeated 5 times. And so we will cover that whole area several times within 5 years. Now, exactly when we will cover the full 14,000 square degrees is actually one of the questions we really want to answer during our survey validation. So there was this debate within the collaboration of, do we go wide and shallow start out, or do we go narrow and deep starting out? Because both of those have different implications for how the survey will be run and how we will move forward. For the most part, it's been decided that we will go deep on a couple different areas of the sky and pretty much run through what we'd say like the full 5-year survey on a very small area in the first couple months, rather than trying to get the whole 14,000 square degrees. But I would say within the first year or so, we will cover the whole 14,000 square degrees, just not to the depth that we will finally want to measure it to.
Thank you. That was a really good answer. That was a very detailed answer. Thank you, Parker. And one last question that I'm going to drop in the chat for you to see, and I also can read this here. And I want to say we've had really good audience participation, YouTube chat audience participation. So thank you all so much for that. Okay, so last question here. So the question is, have you ever tried to calculate, and they put quotes, the real contribution of dark energy to the total density of the universe without dark matter, just with the baryonic matter?
So I actually have, because it's a requirement in many cosmology classes in grad school. Luckily, you're not asking me to sketch that out right now. But, there are quite a few kind of foundational equations we use in cosmology to help us understand what would things look like if we had all matter, all dark energy, all radiation, or different components of the universe. And these equations help us develop models that we can compare against the data. And so we definitely have calculated that, and there are many ways to do that. But I think what I want to drill in here is those equations and those contributions, and kind of putting different contributions of dark matter, dark energy, baryonic matter, etc., into these Friedman equations can help us compare the data we're getting to these components. I guess a fairly shaky comparison might be you have a baked good that has certain ingredients in it, and you want to make the exact same baked good, but you don't have the list of exact ingredients, and so you play around with a little bit more vanilla or a little less sugar, things like that, and eventually you find the exact replication of the baked good you're trying to copy, and then you know what went into the original copy. So that's a lot of what physics modeling is coming up with all the possible combinations of things, and then comparing the outcomes of those to the real data that you're getting. So for the person asking about kind of the real contribution of dark energy, I recommend looking up the Friedman equations and digging in there together with general relativity. And we didn't have enough time to cover all of that, but those different components I think will start coming together for you.
Thank you, Parker. Very detailed, specific responses. These are great, and we're getting lots of thank yous, and I appreciate it in the chat, just as feedback to your responses. So thank you so much for that. And we have just to let you know, we have people from checking in from Finland, from Argentina, from La Serena, and from various places in the US. So we are really excited to have you all here. And also a big shout out to all of our NOIRLab colleagues who are also watching. We appreciate your support. Okay, Parker, our last question here is actually a two-parter. And the first is, were photometric redshifts obtained from DeCam? And the follow-up is, if so, how good were those, and how better will the spectroscopic redshift be from DESI?
Good question. So yes, we did obtain some photometric redshifts from DeCam, and they are good, but not good enough to do the precision cosmology that we need to for BAO. DECam is used to study dark energy, comes from the name, but they are really taking images and looking at the shapes of galaxies rather than the redshift. And so a very precise measurement of redshift is required for DESI. So the photometric redshifts from DECam can kind of give us an idea of where are these galaxies in the Z component, or how far away are they from us. But we won't know their exact redshift until we get them spectroscopically. Now, the exact difference, I don't know the precision to which we get the photometric redshifts, but the spectroscopic redshifts are within kind of 1% type measurements, so extremely precise, and that's really what we need to get with DESI. So it's a good first step with DECam, and their images are very useful in studying certain aspects of galaxies, but not for the very precise cosmology we're doing with DESI.
Well, thank you very much, Parker. That was fascinating. And I actually have some more questions about DESI right now that I didn't know I had before, because I learned some new things. So, but I have access to you offline, so we don't have to do that right now. But I just want to make a quick announcement. So I'd like to thank you again before we go. I would like to make a quick announcement that starting in October, the time we're going to be doing the time is going to change for these live from NOIRLab events. We're going to do it at 5 p.m. local time from each of the sites. So the Chile one come from 5 p.m. in La Serena, Tucson 5 p.m. in Tucson, and Hawaii 5 p.m. in Hawaii. We're doing that so people can watch after work. So be sure to watch our Facebook page and Twitter accounts and social media accounts so you can see what the time is and the topic is for each week. And next week will still be at the same time. Last one at this time, Jamika. It's coming from Gemini. Would you like to tell us about next week's program?
Yes, absolutely. So next week, thank you, Rob. Next week, for live from Hawaii, we will have two guests. We will have Jesse Ball and Jose Cortez of the Science Operations Specialist Group, here to talk about science operations at the International Gemini Observatory here in on the Big Island of Hawaii, on Mauna Kea. And of course, Gemini is a program of NSF's NOIRLab. And so we are very much looking forward to sharing with you all. As you can see from my background, this is a view from the inside of the dome here at Gemini. We're looking forward to talking about nighttime operations, Q observing, and our instruments. So thank you so much for that, Rob. And we look forward to seeing all of you again here next week.
Thank you, Jamika, and thank you again, Parker. And we'll say goodbye and see you next week on Live from NOIRLab.